In this video, I would like to explain why the eigenvalue-eigenvector method works for solving systems of differential equations. So let's take the same problem as the previous video. Solve x prime equals ax, where a is 7 minus 3, 10 minus 4. I would like to recall, what did we find? So recall, we find that there are two eigenvalues, lambda equals 1 and lambda equals 2, with corresponding eigenvector 1, 2, and then 3, 5. And then what was our general solution? It was just x of t is c1 e to the eigenvalue t times eigenvector plus c2 e to the eigenvalue t times eigenvector. Another question is, why is this true? Okay. So kind of why this works. And by the way, so I will just give you an idea of why this works. The full details are in the lecture notes. But essentially, it works because of this process called diagonalization. So in a previous lecture, we found that once we find the eigenvalues and eigenvectors of a matrix, we can put it in a nice form. So from the last lecture, I think, from the last lecture, we know that we can write A equals PDP inverse, where D is a matrix of eigenvalues. I believe 1, 0, 0, 2. And P is the matrix of corresponding eigenvectors. So I think 1, 2, 3, 5. And remember, the interpretation of this was A is like D. So kind of like an avatar. And the point is, it turns out this decomposition turns our differential equation into a much simpler one. So it turns out, and again, see details in the notes. See details in notes. That if you define a new function, that if you let, it's a bit weird, but y of t to be p inverse of x of t. And there's a reason we need p inverse, because then it'll make x easier to solve. Then, if you write the differential equation x prime equals ax, just becomes y prime equals dy. Again, here I skip everything. You can see the details in the notes. But if you change coordinates like that, then your original differential equation becomes much easier, because what this becomes, if you write this in terms of coordinates, that becomes y prime of t and then y2 prime of t equals 1, 0, 0, 2, y1 of t, y2 of t, and that just becomes the differential equation y prime of t equals y1 of t, and y2 prime of t is 2 y2 of t. But what's the point of that? The point is this system becomes much easier to solve because it's decoupled. Easier decoupled. Because remember, that was one of our problems with systems of differential equations, where all the functions were jammed together. But it turns out if you diagonalize A, it magically decouples the system. And in fact, what we end up getting is just the basic ODE, where y1 of t is some constant e to the t, and y2 of t is some constant e to the 2t. Again, that's our equation, y prime equals ay. But this is not y, we want x. And for this, we just use that y is p inverse of x. So I think that was step 3 now, yeah. Step 3, solve for x. So remember, y of t was p inverse x of t, and so x is p times. So if you just multiply both sides by p, you get x is p of y. Like Peyam, you know, again, what a coincidence. And this becomes, so P was our matrix 1, 3, 2, 5, right? The eigenvector matrix. Y, we just solved it. So C1 e to the t, C2 e to the 2t. And then if you just multiply a matrix by a vector, you just do it by column. So this becomes C1 e to the t times 1, 2 plus C2 e to the 2t times 3, 5. And that is your solution x of t. So this is really nice, okay, for 2 reasons. First of all, you see where the eigenvalues and eigenvectors come in. So the eigenvalues, they come from this matrix D. And the eigenvectors, they come from the matrix P. So once again, eigenvalue. Vector. And more importantly, it illustrates the power of linear algebra. Because what did we have? We had a completely coupled system that was hard to solve, but using this diagonalization, we effectively decoupled the system. And we'll only be able to do that because of the beauty of linear algebra. So how cool is that?